All right, so in this video, we'll take a look at some of the example questions from our ALEKS topics for this week, which deals with ionic bonding and ionic nomenclature. So the first question here looks at predicting the formula of binary ionic compounds. So just as a quick reminder, binary means made up of two. Components. So we're looking here at predicting the formula of at least 4 binary ionic compounds. All right, so for an ionic compound, you need both a cation. Cations are positively charged, and we also need an anion, which is negatively charged. So it's up to you to decide, well, what are the combinations? So let's take a look. Let's find a cation first. So we have a calcium, be the first one, and let's say the Br minus is the second. So when I combine these, as we saw either in the videos or in lab, we can combine them simply by writing out the formula. We list the metal first, non-metal second, and then we can do our cross-charge method, which is a quick shortcut method to come up with the formulas. The 2 as the charge on the calcium becomes a subscript on the bromine, and remember -1, so the 1 here on the bromine becomes a subscript on the calcium. 1 is understood, so our final thing here can be CaBr2 as our first one. So if I enter that in, we'll do Ca, and then I'm going to click on the subscript. I need 2, and then we need, oops, sorry, we don't need 2, we need Ca, and then we need Br, and then we need 2 as the subscript, put that in. And then if I need, well, I need 4 of these, so I'm going to separate it with a comma, and then I can go ahead and write out the other ones in the same way. So you want to choose you can choose the same cation, just choose the different anion now. So you need calcium combining with the sulfide, the S2 minus. You approach it the same way. Remember also when you write your ionic compounds, you want the formula that must be the smallest, or the formula must be composed of the smallest whole number ratios. Okay, so for example, excuse me, what I mean by that are the subscripts must be the smallest whole numbers or the smallest integers. So for example, if I combine the calcium ion Ca2 plus with the sulfide S2 minus, write my combination, metal first, non-metal second. I can do my cross-charge thing. So the 2's swap places, so I end up with a 2-to-2 ratio. The subscripts, excuse me, 2-to-2 is the same as 1-to-1. So the simplified version of that would be CAS, right? To get to the smallest whole number ratio, you can divide both of these by the smaller of the 2. So if I divide both of them by 2 in this case, that's how I end up with 1 as my subscript. I don't need to put 1. They're understood to be there. All right, and now we'll take a look at naming binary ionic compounds. And this is part and parcel of this whole topic known as nomenclature, which is just simply going back and forth between the names and the formulas. So we can maybe do the first one. So we have Na plus and we have Cl minus. The first thing that we need to do is to come up with the empirical formula. And the empirical formula, again, is nothing more than the simplest whole number ratio, the smallest whole number ratio, which are the subscripts in the formula. So if I have Na plus and Cl minus, remember the ones are understood to be there. You can write the formula again. So NaCl, do our cross-charge thing. So obviously these are going to combine in a 1-to-1 ratio. So I end up with NaCl. There's nothing smaller than that. So I have Na and then Cl as my formula. And we need to name this. Okay, so for your ionic compounds, as NaCl. We name it as it's written. The metal first name, we just name it as it is. So that's sodium. And then Cl, which is by itself would be called chlorine, but now it's actually part of this ionic compound. We need to drop the ending, replace with IDE. So the correct name for this would be sodium chloride, which is more commonly known as table salt. But in terms of the systematic naming, that's what we would write, sodium chloride. All right, so now we're given formulas and we need to figure out the cations and anions that make up each of the ionic compounds. So really what we're trying to do here is to figure out what are the components of these things. So for example, let's do the second to last one, Vi3. Okay, so we're going to take this and we're going to break it into its ions. That's what we're trying to do. Break into ions. So if you don't know what one of these things are, you can always look at the other thing. Okay, so here we have, you can maybe recognize this I as the iodide ion. And remember now, iodine is in group 7. And it's a nonmetal, so then the charge on a single iodine ion would be equal to the group number 7 minus 8, right? That's our shortcut for determining the charges on our anions. That gives -1 as my charge. So this is made up of the iodide ion, and we have 3 of these, right, based on the subscript. So all iodides in this formula, all 3 of them would add up to give -3, because I have 3 of them. Now, for your ionic compounds as a whole, these overall must be neutral, which means the total positive charges must equal the total negative charges. Well, we just figured out all of the negative charges add up to -3. That's for this half of the compound, which means in order for this thing to be neutral, the other half of it, which is the V, the vanadium, that must be equal and opposite to the negative side, right? So if the total negative charges is equal to -3, then in order to cancel out, the total positive charges they have to be equal to +3. And we only have one V, one vanadium, so that means then that the charge on the vanadium must be +3, right? So we do a little bit of math on that one to figure it out. All right. All right, so in this one, we're given a pair of elements, element 1, element 2. We first of all need to decide whether it's going to form an ionic compound or not. And if it does, we need to write the empirical formula and then name it. So it does encompass some of the similar concepts as a couple of the earlier problems. It just kind of combines them in one question. So let's take a look at maybe the first one. So we have sulfur. So we need to find these on the periodic table. So sulfur is S, and then rubidium is Rb. So if we locate them on the table, we'll see that sulfur is it's a non-metal. It's on the right side. And then rubidium, Rb, is a metal. It's on the left side. So if we have a non-metal and we have a metal, then we can say, yes, these will form an ionic compound, because in ionic compounds, we usually need metals and non-metals. So what would be the formula for this? Well, again, we focus in on sulfur. Sulfur is in group 6. So then the charge on the sulfur ion will be 6 minus 8, which is -2. So the sulfur ion, S-2 or S2 minus. And then rubidium, if we find rubidium on the periodic table, Rb is in group 1. Okay, so its charge then is going to be Rb plus 1, right? So it's simple, fairly simple when it comes to determining the charge on our main group metals. So we're going to combine these now in the simplest ratio possible. When you write the formulas, you always put the metal first. So Rb goes first, and then sulfur goes second. I'll write them separately to start off with. And then I combine them, RBS, and we just do a cross charge. So the 1 on the rubidium becomes the subscript on the sulfur. The 2 on the sulfur becomes a subscript on the rubidium. So we clean it up. We end up with RB2S as your empirical formula. We need to name this. Okay, so we name it as we see it. First name is RB, which is rubidium. And then sulfur as a last name is going to be sulfide with a D. So if you're given or if you're provided with elements that are unable to form an ionic compound, then we need to reflect that in our answer. So for instance, if we look at oxygen and chlorine, okay, we find them on the periodic table where O and Cl are located. These are both actually nonmetals. Okay, and in order to form an ionic compound, you actually need a metal there. So then this will not form ionic compound. Okay, so we'll select no for that one. And there's nothing else to fill in on the other side. All right, so now we're looking at identifying some of the common polyatomic ions. So there are several of these that are not on the list that are in the video that you need to memorize. However, there are some of them you can actually easily locate either in your textbook or in the ALEKS data tables here on the right side. Okay, so you're either given the name and you have to come up with the formula, or you're given the formula and you have to come up with the name. So some of these you need to memorize, others you can look up. So let's take a look. We don't need a calculator, we need the data. And if you scroll down to, I'll show you where to find some of them. They're obviously in your textbook in this particular chapter in your text, but you can also locate them here if you don't want to open up the text. If you go to ionic compounds in water, you actually have several of these listed. So if I can pull these over to the side up here. So for example, if you look at, do you have any of these? Yes, so sulfate, for example, is the SO4 2 minus. So you type that in here. See, we can type that in. So SO, and then we need a subscript. So SO4, and then we need a superscript, and that's 2 minus, which is sulfate. Some of the other ones are located here as well. If you look at, what do we have? We have sulfate, bromate, amino4. So some of them are not on here, which is okay because you can actually find the other ones in their general solubility rules. Okay, so here you can find some of the other ones we talked about, where you have the ammonium ion, NH4 plus. That's also here. You would type in ammonium in that one. So either keep this window open as you're going through, or have your text open and you can quickly go through these. Also keep in mind that there is a list of polyatomic ions that you need to memorize, and that is in either the second or the third video for this week. All right, and now we'll take a look at how we can come up with the formula for our ionic compounds that have some of the common polyatomic ions in them. So this is the same process as we did at the beginning in determining the ionic formula for binary ionic compounds. The only difference now is that some of these are going to contain these polyatomic ions. Okay, so the first thing that we need to figure out is what are the formula for the polyatomic ions and what are their charges. So we're actually given the different ions here. We just need to combine them in the correct ratio. So let's take a look at a couple of these. And the same rule applies. If we want to determine the formula for ionic compounds, we need a positive ion and we also need a negative ion, right? So we need a cation and we need an anion in order to combine to make an ionic compound. So let's just select a couple of these. Let's do we'll do the NH4 plus, and then we have the SO4 2 minus. Right, so you have a positive cation, we have a negative anion. So when we combine these, we're going to, again, write out the formula, and you always put the metal first and the non-metal second. Well, do we have a metal here? We actually don't, but we do have polyatomic ions. So a much more general rule when it comes to writing ionic compounds, you always place the cation first in the formula. Okay, and metals tend to be cations generally. Here we don't have a metal, but we do have a cation. So we have our NH4, and then we have our SO4 that comes after it. What I would suggest that you do is, if you've noticed or if you realize, if you recognize the fact that you do have polyatomic ions, go ahead and surround them with parentheses so that if you have to assign a particular subscript, we're going to know where that subscript has to go. Okay, because it can be slightly confusing if you forget to use your parentheses. So let's take a look. The charge on the ammonium was +1. So the 1 then becomes a subscript on the sulfate, and it would have to go on the outside of the parentheses. And the charge on the sulfate is 2 minus. So this 2 then would have to go on the outside of the parentheses for the ammonium. So the NH4 and then 2 times. Okay, if you didn't have the parentheses, then that formula wouldn't make sense. So let's clean this up a little bit so it looks a little bit more presentable. So we have our NH4 in parentheses, and we have 2 of them, and then we have our SO4. Okay, because you only have 1 now of the SO4, then you can go ahead and remove the parentheses if there's only 1 of that polyatomic ion. And you only need the parentheses around the polyatomic ion if you have more than 1 of that ion. So that's why we don't need it around the sulfate, but we do need it around the ammonium. Okay, so the others are going to be the same thing that we're doing here. This is probably the most complicated out of all of the combinations. You want to approach them the same way.